Hello, everyone. Warm welcome to today's ArangoDB online meetup. My name is Jana. I'm a part of the marketing team here at ArangoDB. And yes, I would like to welcome you to the presentation today. So before we proceed, a quick introduction from my side. Today's online talk is part of the ArangoDB Community Pioneers Initiative. ArangoDB Community Pioneers are all of you guys who are contributing to our open source project. If you would like to contribute, you can do a talk at our online meetup. You can write a blog post or a tutorial or a use case. You can also write us a quick review on G2 Crowd and tell others what you think about ArangoDB. So if you would like to participate in this initiative, I described it a little bit more details in a bigger announcement last time. So please get in touch with me. Here's my email address. It's jana@arangodb.com, or you can also always ping me on Twitter and let's chat. And I'm sure we can figure out something great that you can do. But I don't want to keep you waiting for too long. So let me introduce Aditya, who is our next ArangoDB community pioneer. And he's today live from India. And he's gonna talk about a really cool project that he's built with ArangoDB, which is called the RecallGraph. It's a versioning data store for time variant graphs. But I will also let Aditya to do a bit more deeper introduction of himself and obviously proceed with the talk as well. So yeah, Aditya, warm welcome. Thank you so much for joining us today. And I give the microphone over to you.
Thank you, Jana, for the introduction. Let me just share my screen with you. Okay, so I hope you all can see my screen. Right, so thank you all for joining in. My name is Aditya Mukhopadhyay. I am a full stack developer based in Bangalore. And I often dabble into open source projects. And today I'm going to talk about one of my latest open source projects named RecallGraph. So before we begin, I'll just quickly go through the agenda for today's talk. I'll start with the introduction to the concept of bitemporality, followed by a brief foray into RecallGraph's features and advantages and what are its plans for the future. And I will follow this up by a little bit of a deep dive into the architectural components of RecallGraph, its potential use cases, and finally, I will wrap up this talk with a demo using some data on a sample server. All right, so let's begin. So where did the inspiration for RecallGraph come from? Basically, I have worked in the past with event stores and graph databases in separate context in different projects. And I came to appreciate independently the value that each of them brings on board. And it occurred to me, the thought came to me that what could happen if we could somehow manage to combine both? If we could package the benefits and the power of an event store and the power of graph traversal all into one single solution. And this is where the idea for RecallGraph came from. The primary driving point here is to be able to offer a database storage solution that significantly offloads the complexity and heavy lifting of keeping track of historical changes to data and let the application developers design their applications from a much simpler perspective. So that's where the inspiration for RecallGraph came from. So to begin, I will go through a few key concepts. Um, an introduction to temporality. In the most general sense, temporality means the essence of having a relationship with time in some way or the other. So with that definition in mind, we can consider most databases to be temporal in a sense, because most databases at the very least can record the timestamp of when an entry was created or last updated. Event stores take this a step further, basically by keeping track of each and every update that any entry has or any record has gone through, and thereby enabling point-in-time lookbacks. so that you can query the event store for what a particular record looked like at any point of time in the past. And event stores do this by recording a series of events, and those events are time-stamped. And these timestamps are generally what is referred to as the transaction time. To be more precise, transaction time refers to the physical time or the real world actual time when the record was inserted into the database. So event logs, together with their transaction timestamps, represent a complete track record or a complete history of each and every change that a database has gone through. And this is very useful for building audit trails as well. I should probably point out at this juncture that many databases support bin logs, which can do something similar in terms of rebuilding the state of a database to a point in time. But event logs make things much easier to work with because they simultaneously make all states, all temporal states available just by means of a query. And therefore, they are much more accessible and much more easier to work with than something like a bin log. Transaction times have a couple of properties that are common to all systems that exhibit these characteristics. For one, they are indelible. So whenever there is an entry made into the database, whenever there is a record stored in the database, its corresponding transaction logs cannot and should not be removed, except in cases where there may be security or privacy compliance concerns, in which case the entire event trail needs to be removed at once. You cannot selectively remove events for a particular record. So in that sense, event logs and their corresponding transaction times are indelible. And secondly, they are immutable. Once a transaction time has been recorded and once an event has been recorded along with it, you cannot go back in time and change it in any way. So with these two properties, transaction times and event logs support a lot of use cases, but there are a few limitations. For one, let's say that there was some incorrect entries made into the database, and we want to go back in time and erase those incorrect entries. We don't want to overwrite them with new entries. We want to correct what was incorrectly entered in the past. But due to transaction times and their event logs being immutable, this is something that we cannot do. Secondly, you cannot support multiple timelines. There is one and only one linear timeline that an event trail can support, provided your database only supports transaction time. And finally, you cannot write your records preemptively or retroactively, meaning that the effective business time of the record always has to be the same as the transaction time, or if it is different, the database does not intrinsically understand it. So basically, that need brings in the need for a second time dimension. Uh, so what happens is many real world updates do not happen in real time. As an example, let us say that you are importing certain legacy data from an older system into the newer system. So obviously, in this case, the transaction time is not going to be the same as the business effective date of the data that is being imported from the legacy system. Updates can happen retroactively or in some cases preemptively as well. So to deal with this, we need a second time dimension that represents the time from which a business entity effectively becomes valid. And this should be independent of when it was actually entered in the database. So now we need two independent temporal dimensions. And this second temporal dimension is what we are going to refer to as the valid time. There is a special case, however, wherein the valid time and the transaction time can be considered for most practical purposes to be nearly the same. And this is the case in real-time systems. So finally, any system that intrinsically understands and tracks both transaction time and valid time dimensions is considered to be bitemporal. So when do we need bitemporality? Uh, Bitemporal systems can be primarily used in a lot of situations where historical records of data are important, but I will just go through a couple of instances. So for one thing, we can build very accurate real-world representations of our business data, wherein the business entries can be made completely out of sync with the actual time of entry. So the business effective date differs from the transaction time. and we can keep a very clear track of this. The second thing it enables is higher transparency and clarity, because now we are able to keep track of who has made what changes at what time and what were the contents of those changes. And this basically enables unprecedented transparency. We can also build very interesting analytical and predictive models on top of historical data that has been labeled with two independent time dimensions. And last but not least, we have the benefit of higher data integrity, because with the bitemporal system, you can in fact go back in time and rewrite an entry that was incorrectly inserted, which basically gives rise to an entirely new timeline, while at the same time it preserves the older incorrect entry for record's sake, or building an audit trail of a now obsolete timeline. And you can do this because, unlike transaction times, valid times are mutable, just like any other business or domain specific attributes should be from a database's perspective. So let's go through a couple of examples. Um, Consider a analytics company which calculates credit scores based on other companies' financial statements. And these credit scores are used, for example, by retail investors to make certain investment decisions. Now, this need not be the only signal on which they base the decisions, but this can be one of them. So, an analytics company gets a company's financial statements and builds a credit score based on that. And as it every so often happens in the real world, that these financial statements sometimes get revised. If that happens, then obviously the credit score has to be recomputed. But you cannot just simply discard the old credit score, because some investors may have already made their decisions based on the old score. And therefore, you need to provide a complete track record of what the input was that was used to build the older credit score. It's not sufficient to just have the older credit score in place. You also need to be very transparent about what input you use to calculate that credit score. And now this becomes a piece of cake, because a bitemporal system can provide you with not only the current data, but also the historical version of the data based on which the older score was computed. Second example can be in the domain of e-commerce. So e-commerce sites maintain their product catalogs, and there are a lot of inbuilt relationships, products um, connected to categories, products having their variants, products tracking their inventories, and so on and so forth. Now let's see that the e-commerce website is planning for an upcoming flash sale, and for that flash sale, they want to alter product prices, and they probably want to play around a little bit with the available variants that are there in the inventory for the duration of the sale. And they want to keep all this information ready much before the actual sale takes place. And now they can do this preemptively and not worry about these new prices suddenly reflecting in their system before its time. Uh, and that is because these new entries have been made with an appropriate effective valid date. So they made these changes, and as soon as the campaign start date begins, without requiring any change to the application layer whatsoever, these new prices are immediately reflected in the system. And they can be also set in such a way that when the campaign ends, the new prices stop being effective and are again replaced by their initial or their older prices. This kind of also leads to better seller accountability, because sellers do keep changing prices of their products, and they do so sometimes with unscrupulous intentions. But now there is a complete track record of all their activities and all the changes that their product prices have gone through, giving rise to much more better transparency. And this is also a way that enables better sales analytics. So a little about RecallGraph. It's a Foxx microservice, and it supports ArangoDB version 3.5 and upwards. It has a version control system like semantics in a lot of its interfaces. And people familiar with Git would instantly see those similarities when they start working with RecallGraph's API. It is backed by a transactional event tracker. So any write operations that are carried out through RecallGraph's API are always carried out within the scope of an ACID transaction. RecallGraph obviously allows temporal point-in-time queries. There is one thing that I need to point out here at this moment is that RecallGraph is not yet fully bitemporal. Um, Support for transaction time is completely ready and working, whereas valid time is support for valid time is under development. RecallGraph is open source and it has an extensive test suite that currently uh, boasts of 85% code coverage, and I am working to get that number as close to 100 as possible. So let's go a little bit into the API categories of RecallGraph. It's basically split into three different categories. The first category is the document category, which is essentially the CRUD API minus read operations, because reads in RecallGraph are necessarily temporal by nature, and therefore I have created an entirely different category for them. So all the write operations, create, update, and delete, are contained within the document API category. The second category is events, which, and this is where it bears the most similarity with version control systems. You can fetch logs, you can see diffs between two consecutive versions or multiple consecutive versions of documents. And these APIs are also designed to support a variety of aggregation, filtering, and sorting capabilities. Finally, the history category is where all of RecallGraph's read operations reside. They're all temporal operations, so you can perform point-in-time lookbacks for individual nodes or a collection of nodes. And also you can run point-in-time traversals for a past version of a graph. RecallGraph exposes all its API endpoints through REST interfaces. Another interesting thing is RecallGraph does not pollute the user's data with any of its own service metadata. So the user can always go back and look through their collection data in the web console or through any other means. And they'll always find a pristine and clean view of the latest version of their data. And this is, again, in some ways similar to Git, wherein if you have a local Git repository, basically Git working tree, you can see that your files and folders, to a large extent, not uh, they are not polluted. The folder structure is not polluted with too many of Git's own bookkeeping files. Most of the stuff is in a top level .git folder. And RecallGraph does something very similar. So it does not insert any of its metadata into any of the user's collections. It supports ACID transactions currently only on single server instances. So as and when ArangoDB, and if it is possible, it starts supporting distributed ACID transactions, so will RecallGraph. Now, RecallGraph has uses an event log to keep track of changes to all the content of all its vertices and edges. And it has something called a skeleton graph that records the structural changes or the change in relationships between entities in the graph. And these last two components we will go into a little bit more in depth in the upcoming slides. And finally, it has a complete support for transaction time built in, and with support for valid time coming up very soon. All right, so now let's take a closer look at the event log and how it works. And for that, we'll use the example of a pet named Anna. Anna likes to sport a new look every season. So whether that is a change in her hair color or chooses to use an accessory, different one every season. So we'll see how RecallGraph is able to keep track of these changes. So we start with the spring of 2019, where Anna sports black hair and no accessories. And in the summer of 2019, she decides to add a pair of red glasses. So let's see how RecallGraph can keep track of this. Initially, an object is inserted into RecallGraph's event log, which represents the entirety of the contents that represent Anna. And when we want to represent the update that happens, we only track what has changed. So the only thing that has changed from spring to summer is a pair of new red glasses have been added, and RecallGraph only keeps track of that. Then in autumn of 2019, Anna decides to dye her hair blonde, and RecallGraph just tracks the change in hair color. In the winter of 2019, Anna changes her spectacle frames from red to black, and RecallGraph keeps track of that. In the spring of 2020, Anna loses her glasses, and so RecallGraph tracks that as a delta going from black frames to nothing. Finally, in the summer of 2020, Anna changes her hair color to purple, and that is also tracked by RecallGraph. So now that we have an event log which stores all the changes that a object has gone through in the form of a series of deltas, we can answer questions like what look to Dana Sport in the winter of 2019. And one way in which RecallGraph enables this is by replaying its event log from the very beginning, going through all the changes in the form of deltas that have occurred till the point of winter 2019. And we basically rebuild her look as of that particular point in time. But there is a drawback to this approach. Provided the number of events is very small, it's fine to replay all the events from the beginning, but a node may very well have gone through hundreds of changes. And if you want to rebuild its state at somewhat later stage in its lifespan, in its life cycle, replaying hundreds of events is going to be an expensive operation. So RecallGraph has provided a means of mitigating this by means of something called snapshots. Snapshots are nothing but a complete picture of the entire state of an object, and these are taken at periodic intervals after a certain number of events have occurred. In this example, at every 3 events, there is a snapshot being taken. So now, once again, we want to rebuild the state of the object as of winter 2019, and this is now done very simply by finding the nearest snapshot, and from there, we just have to replay one event to get the state as of winter 2019. There is another thing that RecallGraph can do, and that is it can play snapshots, it can play deltas in reverse. And what it does basically is take the example of spring 2020. We can here see visually that it is actually a snapshot in the future, which is closer to its point in time. And RecallGraph can perform shortest path analysis to figure out which is the nearest snapshot, and that may be at a point of time in the past or a point in the future. In this case, it takes the snapshot which was taken just after the summer of 2020, and it figures out what are the events that need to be replayed to rebuild the state back to 2020, with the only difference being that the events are played in reverse order and the individual events themselves are also reversed. The deltas themselves are also reversed. So the event log in RecallGraph stores its deltas in such a way that they can all be reversed. So that's more or less it about the event log. Now let's move on to the skeletal graph and what we achieve with it. Here we see on the right side the object graph, or basically the user data. There are two objects already in place, and they represent two employees in an organization. That's Ted over here and Lisa over here. And correspondingly, RecallGraph keeps track of these two objects in its skeleton graph by creating two vertices, one for Ted, one for Lisa. Now, these two vertices do not contain any information about the content of the object graph. All they track is the object ID or the vertex ID and when it was created. The same for Lisa. So let's say that a new member joins the organization. Let's call her Rose. And RecallGraph basically adds another entry in the skeleton graph to represent that entry creation. Now, suppose we want to establish a reporting relationship between Rose and Lisa by creating an edge going from Rose to Lisa. And essentially, in this context, it means that Rose has started reporting to Lisa. Now that will be represented in the skeleton graph in a slightly different way. It is represented by means of a triple of a hub and a couple of spokes. And I'll get to why it is represented this way in just a minute.
Aditya, are you still there? I think the video got frozen for a second. Can you guys still hear me though? Let's just give Aditya a few seconds because I think he might have lost his connection. Test, test, test. Technical difficulties that sometimes happen when you're doing live video. Just 1 second. Okay, we're back online. Hi, Aditya.
Hey, thanks. I got disconnected. Sorry about that.
No, no problem at all. Okay, so we will just continue from where we left off, okay?
Sure. So let me retrace my steps a bit. So we are trying to represent a change in the reporting relationship where Rose stops reporting to Lisa and instead starts reporting to Ted. This can be represented in one of two ways. One is where the original edge is deleted and a new edge, a fresh edge is created in its place. And the other way is wherein the edge is retained, its ID remains the same, and its source remains the same, and the only thing that changes is its target. So it is the latter which I'm going to represent here in the skeleton graph. So this edge has basically moved its destination from Lisa to Ted. So to represent that in the skeleton graph, let's, okay. So, and the existing edge going from the hub to Lisa is invalidated, and it is invalidated by assigning a non-null end date type to it. And in its place, a new edge is created going from the hub pointing to Ted. And here the end date time is kept as null. So in the skeleton graph, any component which has a null end date time is considered to be valid as of right now. So this hub and spoke model basically allows us to move our edges around without necessitating, retaining their ID. One single hub always corresponds to one single edge as long as the ID remains the same. In the other instance, in the other scenario, if in fact this operation was represented by a delete followed by a fresh insertion, then this entire triplet would have been invalidated, and in its place, a new edge and spoke group would have been created. So now let's say that Lisa decides to leave the organization. So we need to dismantle her reporting structure first. So this reports to edge gets deleted from the object graph. It is correspondingly represented in the skeleton graph by invalidating uh, both the spokes and the hub that represented that edge. Finally, the vertex representing Lisa is marked as invalid by assigning an end date to it. So that's how the skeleton graph works. So what are the potential applications of RecallGraph? Basically, any system where it can be an analytical or a transactional system where historical versions of the data are as important as the current data. So they are to be considered as first-class citizens. You can find a use for a Bitemporal system, RecallGraph being one of them. And of course, if the data sports the characteristic of being highly connected, so RecallGraph gives you the additional benefit of supporting graph operations in the form of point-in-time traversals and also point-in-time shortest path lookups. The advantages of RecallGraph, it's quite easy to install and get started, as are most Foxx applications. Bitemporality supports a wide range of real-world applications where historical data versions are important. And snapshots allow for rapid rebuilds from the event log, as we have seen in a couple of slides ago. User collections are completely untouched or unpolluted by service metadata. So you always get a clean and pristine view of the latest state of your data. It supports quite a few advanced querying capabilities, and these are constantly being built upon and improved so that you can see more and more capabilities as time goes on. And it significantly reduces the design and development complexity for temporal applications. So now an application or a database designer no longer needs to worry about designing a schema that is explicitly intended to keep track of all the changes that their data have to go through. And nor do the application developers have to deal with it. So it is all abstracted out for them. As we have seen, it is quite efficient in terms of space storage because it only stores changes in the form of deltas, and it rather than storing entire object copies for every single version of every single node. Okay, so now we're going to switch over to a quick demo wherein hopefully I will be able to demonstrate RecallGraph in action. So before I jump to the demo, let me take a little bit of time to explain the nature of the data that I'm going to work with. This data has been pulled from a travel portal website. And in that website, you have information about flights going from a certain source to a destination, the flight dates, and the flight prices. And in my system, I have uniquely identified a flight using its flight number and its date of departure. And as you can imagine, every time a user searches and this flight shows up in their search results, from time to time, certain attributes of a flight can change. Most often, it could be the price, and sometimes its departure time may also change somewhat. And these flights are represented as edges in the database, so it is the change in the contents of these edges that I will primarily track in my demo. Other than this, it has a few vertex collections, one representing airports. Airports have a few basic fields, and as you can see in any of you can pick any random vertex, and you will see that there is no additional metadata that RecallGraph uses for bookkeeping. None of that metadata has spilled over into the contents of this node, but it is still being temporarily tracked. So yeah, it has airports, it has cities, it has countries, and respective ownership relationships between them. And it is the life cycle of changes that individual flights go through that this demo will be primarily based on. So to start with, I'm going to run a quick aggregation query to help me find out which flight has gone through the maximum number of changes during its existence within my database. And of course, I mean, I've just pulled a small sample of the data from the travel portal. It's not the travel portal's data dump that I have with me. And here we see that this particular flight has gone through the maximum number of changes. It has gone through 10 changes, which effectively amounts to a create followed by 9 updates. So what I'm going to do next is I'm going to fetch a list of all the events along with their timestamps, which represent these changes. And I don't need to copy and paste the flight ID or anything. I've just done some scripts in my Postman client to keep track. So I'm waiting for that information to come through. So what I have here is a list of events in chronological order that represent all the changes that the flight has gone through. And they just represent the events. They are not a record of the deltas. So as you can see, the first event that happened is obviously a creation event. And this records the Unix timestamp. And this is essentially the transaction time that RecallGraph works with. This created event would be followed by a number of updated events. And in this case, I'm expecting a total of 9 updated events. You don't need to count them. And the reason I fired this query is to let Postman make a record of all these transaction times. So that now what I can do is I can rebuild its state at various points of time. I can cycle through uh, this rebuild query a few times, and every time it will rebuild at a different point in time. And I will take the content of this. I will paste it into a diff tool. I'll just clear this out. Okay. All right. I paste this into a diff tool. Then I fire this a couple of more times, and every time it fires, it basically queries at a different point in time and rebuilds the state as of that point in time. Let me do this one final time, and we'll see if we can detect any differences. So yeah, instantly we see anything that is represented using a colored band is a difference. Uh, these dates, expires at, return at, they are not intrinsically processed by RecallGraph. They are just like any other field. So they are valid in the business context, but RecallGraph does not process them in any special way. So yeah, but we can see that they are changed. Sometimes, the return date has changed a bit. But what is most interesting is that the price has changed. So at the time it was created, the price was $107, and all prices are stored in dollars here for consistency. At a later point of time, the price has gone up to $213, and in the future, the price has gone up to $324. And in all cases, we see that the ID is identical. And in fact, this stiff tool makes it very easy to note that, because otherwise this would have been a colored band as well. And it is the same ID, the same key, and you can see that the revision number has also changed. So we are looking at three different versions of the same node at different points in time. So this is one way in which you can see how multiple versions of the same node are tracked. So now let's move on to another demonstration wherein we can probably run a traversal from point to point and see how the results of the traversal change depending on what timestamp we feed into the query. So I'm just running a query that fetches me a list of all connecting flights from the city of Bangalore, which is where I live, to a city named Indore, which is a city in central India. And we are not going to go too much into the details of these results. These are again just meant for Postman to populate certain flight IDs. Now I'm going to run a second query that will fetch a list of the creation time for all those flight IDs. Once again, this is not for me. This is more for Postman to populate its environment with a bunch of timestamps. And yeah, so I think Postman has recorded all of that. So now I'm going to fire a query which is asking for a list of uh, connecting flights from Bangalore to Indore, whether they are one hop or two hops, and sort them by in ascending order by prices, and give me the return the top 5 results. So, and it is doing that using a timestamp value that happens to be the latest timestamp value, which was retrieved from the previous from the pre-query. So every time I fire this query, we will see that it runs a query at a different point in time, and hopefully we'll see how things change. Now, I have built a visualization that can help us better understand these results. So let me just quickly explain what's happening here. Here, we are looking at the city of Bangalore. From Bangalore, we connect to Bangalore Airport. From Bangalore Airport, a flight goes to Ahmedabad Airport. Ahmedabad is another city in Western India. And from Ahmedabad Airport, there is a flight connecting to Indore Airport. These flight numbers are given here together with their prices marked in brackets. And the total price is given here. In this case, the cheapest available trip will cost you $109, followed by the next, which is $138, 146, 172, and 191. And let me also just quickly take a screenshot of this so that we can, at a later point of time, do a visual comparison between two different versions of this. So let's say it is download one. Yes, replace. Okay, I'm going to fire this query again, and when I fire this query again, it will actually fire it for a different point in time. These are actually shortest path queries that are being fired inside RecallGraph. I have a different set of results, and it will be difficult to compare this with the previous result until I take a screenshot of this as well. Save it. This I will call normal 2. Yes, thank you. And now let's just see if I can view them. Okay, and let's try to figure out if something has changed. Yes, one thing we can instantly see is that although the cheapest flight has remained the same, the second cheapest flight has this particular trip, this particular route has disappeared. So this $138 route has disappeared. This $146 route was the third result, whereas in this case it is now the second result, and then they have all been promoted up, I guess, by one level. And we can see that obviously the flight number GE 586. Yeah, basically this third row is now identical to the second row, and the second row over here has completely disappeared because one or more flights, one or more connecting flights are no longer valid for the timestamp in which I fired the query. I can also do JSON comparison, perhaps, just to help us see if there are any other changes that we can capture. And let me fire this query a couple more times. So we have seen in the visual comparison already that things are changing, and we'll also do a JSON comparison to see if we can find out something else. Every time in this query, as I said, it is sending a different timestamp parameter to RecallGraph, and therefore we are getting different results. Okay. Let me paste this. And this, hopefully we will get results. There will come a point in time where the timestamp will have gone so far back in the past that one or the other legs of the journey gets broken, and therefore no paths return because there are no available for that leg. Thankfully, I haven't reached that point in time yet, and therefore I can do a three-way compare. And we saw that. Okay, yeah, here we can see some changes. So what has changed here? The flight number has changed, the price has changed, and just in case it happens that these two are completely identical, I could probably fire a query one more time and I'll get a different result. So that also happens sometimes. Yeah, so we can see that things have changed depending on, I mean, I'm running the same shortest path query with the same criteria with the same endpoints, but the only thing I'm changing is the timestamp, and depending on the timestamp, a lot of parameters can change. In fact, right now, if we see the visualization, in one of our earlier visualizations, let me see if I can bring up this and this, we see that all our flights were routed through Ahmedabad, but here, the last two flights are routed from Mumbai. So that's a change that is very obviously detected. Let me run this one more time, and this time I think the path will be broken. Yes, because now no further flights are available. So that's a demonstration of how a temporal shortest path query runs. Finally, let's do something really free form. So we run a shortest path query, and let's just basically run a traversal, starting from the city of Bangalore, going out to a depth of 2. And I have to specify a depth of 2 because first it has to go from the city of Bangalore to Bangalore Airport. And then from Bangalore Airport, it is searching for all available outbound flights. So let's see what we get. And probably there will be a lot of outbound flights out there. If not, oh yeah, there's quite a few. Okay. So let me see if I can play around with this a bit. Let me use a different timestamp and see if that changes results somewhat. So right now, the value of C time for this last query, the value of C time that was used was this one, which is basically the last item in this array. Yes, it is. And now I'm going to use the first item in this array, which is a much later point in time. Therefore, hopefully we'll see a lot more flights available. Just once again, just take a look at this graph. Try to remember, you can't remember exactly how many flights were there, but just try to get a basic sense of how many connecting flights are there. And now let's run it at a later point of time. Hopefully we'll see a lot more outgoing flights. But has something changed? Or maybe I'll just, oh, all right. Okay. Sending the time. I was not sending the timestamp earlier at all. Mhm. Let me just run this one more time. See what we get. Okay. This is, if I don't specify the timestamp, it essentially means as of right now. And if I do specify the timestamp, hopefully I get a different result. Oh, yeah, we do. In fact, the number of flights is reduced drastically. So right there, you can see how things have changed. So that concludes the demo. I mean, we can always come back to it if somebody has a question, but let me just go back to the slides for now. All right, so what's in the future for RecallGraph? I want to provide the ability to query based on relative or absolute revision IDs. And this can only work in case of individual document queries. And relative absolute revision based queries can be the exact revision string. The relative revision queries can be based on 0 representing the latest revision and then going to successive negative numbers, -1, -2, or go further back in the past. I may not explicitly enable branching support, but I might internally use it to make multiple timelines available. One that will happen probably when valid time support is built into RecallGraph. This is again a tentative feature which I'm not yet sure if I will enable, but I think it will be useful. So basically, you define a section of the data, basically a named graph or a collection or a bunch of nodes identified by their node IDs, and you check them out as of a particular point in time. And once they are checked out into their own separate collections, then users can just run ad hoc equal queries on them, thereby getting the full power of getting to use the full power of AQL on a materialized historic version of their data. Another thing called CQRS ES is just another fancy way of saying that I want to provide means through which users can update their nodes by directly feeding in the deltas instead of providing new versions of the node content and having RecallGraph compute the delta. Explicit commits, it could happen in some cases that some data, some collections or some nodes which are meant to be tracked by RecallGraph happen to get updated from external means. So RecallGraph's event log hasn't yet caught up to that change. And an explicit commit would allow it to catch up to that in one single step. Support for ArangoDB clusters as and when ArangoDB enables ACID transactions. I'm not sure if that's really possible, but if it is possible, some form of consistency, then Foxx will also support it. RecallGraph will also support it. And it will be good to have multiple authentication and authorization mechanisms in place. So here's a list of links and references that go much more in depth into some of the topics that I have only very superficially covered in this presentation. They they explain the concept of bitemporality in much greater detail, different approaches to graph database versioning, and also how to go about scaling time version graphs. So I will put up a link to these slides, and if you're interested, you can probably follow some of these links to enhance your knowledge to a deeper level. So with that, I conclude my talk. Thank you all for joining in, and yeah, if there are any questions, please let me know.